I think you're muted.
Very great. So thanks for that. So good. I just want to finish off the proof of the KMR theorem from last time because we were almost done with the proof. We were less than half a whiteboard away from finishing it. So let me do that. I'm going to first remind you of where we were. And then after we do that, I'm going to show you how to use these tools like Dudley's inequality to actually come up with an even better algorithm for the heavy hitters problem. So maybe it's not clear why those two things would be related, but you'll see that in the remaining part of the lecture. Okay, so if you recall, the KMR theorem was this. You have a set of matrices, script A, and plus minus one random variables. The theorem actually holds for sub-Gaussians as well, but we just proved it for plus minus ones. And you're looking at this supremum of a stochastic process. So a stochastic process is just a collection of random variables. Okay, so our random variables here are these differences a sigma L2 squared minus expectation a sigma L2 squared. So each one of those is a random variable, and we're looking at the sup over all of them in magnitude. And there was this theorem that it's bounded by up to a constant factor by this right-hand side, gamma 2 squared plus gamma 2 times the Frobenius radius plus the Frobenius radius times the operator norm radius. And this was related to Gordon's escape through the mesh theorem to get instance-wise bounds for dimensionality reduction, where the target dimension is not log n over epsilon squared, but it's the square of the Gaussian mean width over epsilon squared, right? And the way that we got that from KMR was for each point that we're trying to preserve, we can define this matrix. So for each point x we're trying to preserve, we define this matrix a sub x, which is written here at the right-hand side of the whiteboard. And then we basically will apply KMR to that family of a's. So ax for each x in the point set. Anyway, so let's finish off the proof of KMR. So I defined, let's go to where we were for KMR. Okay, good. So I defined E as being that expectation of the supremum of the stochastic process. Okay. And I said, I denoted the columns of A by A1, A2, etc. And I said that TR is an admissible sequence. If you don't remember what that means, it means T0 has size 1, TR has size at most 2 to the 2 to the R, and the TRs are nested. T0 is a subset of T1, which is a subset of T2, etc., which are all subsets of T. And I defined this notation, pi RA is the closest point to A in TR under operator norm, and delta R is pi R minus 1. Okay, so given all this notation, what we showed last time is E, which is the thing we're trying to bound. We showed that E was at most this thing here. Okay, and we bounded the first term already. We bounded this term already by this. That's the operator norm radius times the Frobenius norm radius. And then our what we were finishing off was bounding like this thing in the middle. And the thing on the right and the thing in the middle are basically the same. I mean, in terms of how they're not, of course, they're not the same, exactly the same, but the way you bound one is pretty much exactly the same way as you bound the other one. So we just focused on the middle there. Okay, what was this XRA? XRA is defined up here. It's this dot product up at top. So delta RA sigma dotted with pi R minus 1 A sigma prime. And then we summed over all R's from 1 to infinity of XRA. Okay, so of this, expectation of the sup over A of the sum of XRA. So that's the thing that we are trying to now understand. So this is going from okay, and basically, we just use the fact. So call this big random variable Z. Okay, the sup over A, the sup over all A of the sum over R of the absolute value of XRA. Call that entire thing Z. Z is a random variable. It's a non-negative random variable because there are absolute values there. And the expectation of a non-negative random variable is the integral of its tail bound. That just follows from integration by parts. We used that last time. right? That was this inequality. That was this equality right here. The expectation of random variable is the integral of its tailbound. And then we just did a U substitution. You remember from, I guess, high school calculus. You do a U substitution. We did that to artificially insert a gamma 2 in there. Okay. I mean, you could say, well, Jelani, if it's artificial, why is gamma 2 special? Why couldn't I have inserted anything else? And the reason is when we put a gamma 2 in there, specifically that thing that's circled a billion times in red, okay, that's beta, and we did the U substitution, U equals T times beta. Or actually, well, I should say that whole thing in the red box, not just the thing that's circled, but this whole thing in the red box was our beta. And then we did a U substitution. We said U is equal to T times beta. And now the point was, after we did that, we could do this like infinite union bound after doing Khinchin inequalities, one for every R. So for each fixed A and for each R, we could do Khinchin's inequality to get a tail bound. And then we could union bound over all A. We could union bound over the entire net, and we could union bound over all the elements of TR, and we could also union bound over all R. And then we would get this circled sum, which was convergent. So that's kind of why gamma 2 was special. It's not like you could have just put anything in there. You need to put something there such that when you calculate the probability that the left-hand side exceeds the right-hand side, you get something that when you integrate it converges to a constant. And it just so happened that this choice of beta made that happen. It made that integral of the probability converge to a constant, so that what you were left with at the end of the day was just beta outside of the integral. So that was why this choice was special. Okay. And then what we said was, look, this is just rewriting more cleanly what was on the previous whiteboard. What we were saying was, I didn't say this explicitly last time, but this is kind of where we left off. So where we left off was basically right here. Okay. And this delta RA, just by triangle inequality, what is delta RA? Delta RA is pi r minus 1. So if you just add A and subtract A and then do triangle inequality, you'll get what I wrote above it in red, namely that delta RA in norm is at most A minus pi r A plus A minus pi r minus 1A. And the TRs could be anything. So if you just choose the TRs to minimize the right-hand side, that is the definition of gamma 2. Gamma 2 is the inf over all admissible sequences of TRs of this quantity, right? So that is gamma 2. And then this is basically now where I want to pick up from, and we're gonna finish this proof right here on this whiteboard. Okay. So how do you finish the proof? First, you just do some Cauchy-Schwartzing, right? So Cauchy-Schwarz says the expectation of A is at most square root of the expectation of A squared. So I'm going to do that here. This is at most square root of the expectation over sigma prime sup over A sigma prime L2 norm, operator norm. This is an L2 norm squared. This is L2 norm. This is a vector times gamma 2. I'm just going to write gamma 2, which you should read that to mean gamma 2 of script A with respect to operator norm. And then now I can do a triangle inequality. I can subtract the expectation and add it back. This is at most, so this square root thing is the same thing as, I think it's just going to be easier for me to write. Square root, I'm just going to say it's like raising it to the 1/2. So this is at most, my triangle inequality, expectation over sigma prime, sup over A in script A of A sigma prime L2 norm squared minus the expectation of A sigma prime L2 norm squared plus the sup over all A of the expectation over sigma prime of A sigma prime L2 norm squared square root times gamma 2. Okay. This thing is also known as, I mean, it's just the trace of A transpose A, right? Does that make sense? I mean, sigma transpose B sigma, this is equal to, this thing here is equal to sigma transpose A sigma, right? Sigma transpose B sigma is the sum over all ij of bij sigma I sigma j. If you take an expectation of that, what happens? When I is not equal to j, I'm looking right here. When I is not equal to j, you get 0 in the expectation. When I equals j, sigma I squared is 1. So the only thing that survives in the expectation is the trace. It's the diagonal terms, right? So this expectation that's boxed below is the trace of A transpose A, which is just the Frobenius norm squared. So then if you take the sup over that, that's the sup over the Frobenius norm squared. That's just equal to the Frobenius radius squared. Okay. And then now you use the fact that, square root of A plus B is at most square root of A plus square root of B. So now what we get is, this is at most Frobenius norm radius of script A plus, if you notice, what is this thing? So it's going to be like this thing square rooted, right? It's going to be this part square rooted. What is that thing that I've just circled in red?
E.
Yeah, it's E. But there's a square root, so it's root E. All times gamma 2. So in other words, if you just put together, this was only a bound on the XR part. Right? Don't forget that there was the YR, which basically gave the same thing. And then there was also this first part over here, which gave us this. Okay. So if you so E was bounded by the sum of all those things. So if you put it back all together, this implies that E is at most up to a constant factor. The operator norm radius times the Frobenius norm radius plus the Frobenius norm radius times gamma 2 plus root E times gamma 2. And let me just name this thing. I'm just going to name this thing Z. Right? So what have we really shown? We've shown that Z squared minus some constant C times gamma 2 root Z minus some constant times df gamma 2. Well, actually, let me just pull the df out. Gamma 2 plus L2 to L2 operator radius is at most 0. That's what we've just shown. Okay. So this is a quadratic equation. And, when Z is minus infinity, it's infinity. When Z is plus infinity, it's infinity, just because there's the constant factor in front of the Z squared term is positive. So, this quadratic equation, if you plot it, it looks something like this. And here, this is Z. And then the y-axis is the Z squared minus whatever. So I just plotted that quadratic equation. This is 0 right here. And what are we saying? We're saying that Z is at most 0, which means that Z has to be smaller than the larger root of this quadratic equation. Z is at most this point, right? Does that make sense? Right? Any questions about that?
Makes sense.
Makes sense. Good. So that's it. You basically just solve the quadratic equation for Z. You look at the larger root. You don't really want to bound Z. You want to bound Z squared, right? Z is root E. We're trying to bound E. So you look at the larger root of the quadratic equation. You square it, and that's your bound on E. And if you do that, let me not do it because it's not really interesting. It's just like a calculation at this point. If you do that, you're going to get exactly what's written here, the right-hand side. Okay? So that's it. That's the proof. If you look at the probability review in the lecture notes, I call this the square root trick. Basically, you have some, usually it's some moment bound, some moment that you're trying to bound. You do some sequence of steps to bound it in terms of its own square root. You solve a quadratic equation, and then you declare that the moment is at most the larger root of the quadratic equation. So there's a proof of Bernstein's inequality in the notes that goes about it the same exact way. And I think there might be, and I think Hansen-Wright also. The proof of Hansen-Wright we also in class did, that was also via the square root trick. So it's a pretty, I think, useful trick. It's a trick that I think was invented by Mark Rudelson back in the late 90s. But it's kind of useful all over the place. Okay. So that's it. And now I want to show you another application of this business of supremo of Gaussian processes or stochastic processes. Okay. So another application, okay, let me just write other. Other applications of bounding supremo of stochastic processes, like Gaussian processes or Rademacher processes. So one is showing that SH satisfies RIP. So here S is a sampling matrix, and H is Hadamard. You can also use the DFT. So if you remember when we proved the Kramer, was it Kramer-Ward theorem, right? That you can take any RIP matrix and get a JL distribution out of it. One of the things I mentioned at the time was that's another way of analyzing fast JL because it's known that SH with high probability satisfies RIP. Therefore, if you throw the D on it, which is the diagonal signs, you'll get a JL distribution. So how do you actually prove that SH satisfies RIP? I'm not sure that we'll have time to talk about it today. If we do at the very end, I can say a little bit more. But basically, you can write down kind of what you want to bound, and then do a few standard tricks to basically turn it into bounding the supremum of a Gaussian process. And then you can use Dudley's inequality. And that's exactly what Rudelson and Verschinen do to show it. There were some sharpenings of the log factors after them. But the basic idea that this can be reduced to bounding the supremum of a Gaussian process was due to them in Rudelson and Verschinen in 2008. Two is getting a lower memory. So, for example, I can say this is due to Rudelson and Verschinen. Lower memory requirements to solve L2 heavy hitters in insertion only streams. So you know that the count sketch uses O of K log N words of memory. And it turns out there's another data structure called the BP tree, which uses K log K words. Remember, you're trying to find the approximate top K out of a universe of size n. So K is always at most n. In particular, if K is a constant, you're trying to find the top 10 or the top 100. The BP tree uses a constant number of words of memory, whereas the count sketch uses O of log n words of memory. And I'll just say it's an open problem. show that O of k is possible. Okay, well, actually, I shouldn't. Well, I don't know that it's true, so I should phrase it a little differently. Is O of k possible? We don't know. And L1 heavy hitters and insertion only streams, we know that you can solve that in 2K words of memory. That was one of your PSET problems on the very first PSET. I think that was the last problem on the PSET, if I remember correctly. But for L2 heavy hitters, we don't know. We don't know whether the right answer is K log K or whether it's K. I mean, we know that there are differences. Like the BP tree is not a deterministic algorithm; it's randomized. Okay, and we know that. I believe that you can show that you need to be randomized for L2 heavy hitters to be able to get anything which is sublinear. Whereas for L1 heavy hitters, that problem on your PSET on PSET 1, you could, if you didn't use the dictionary, if you didn't care about runtime, you didn't use hashing, you could get a completely deterministic algorithm that uses O of k words of memory, right? So for L1, the story is a little bit different. We know that O of k words deterministically is possible. I think that's not possible for L2. The best we have is a randomized K log K. So can you get randomized K, O of K? That's the question. So good. So what I want to focus on for the next for the remaining part of lecture something about the RIP as well. Okay. So, and I guess the reference for this is, well, there were a lot of Braverman, there were a lot of authors. Braverman, Chestnut, Evkin. Yeah, so just remember, if you want to look for it, this is Braverman. I mean, it's going to be in the notes. The reference will be in the notes, but it's from Pods 2017. Okay, great. So let's look at it. So the BP tree. First step, reduce to the super heavy problem. And the second step, show, like, okay, in particular, when I say reduce to super heavy, I'll define, I haven't told you what super heavy means, but I'll tell you. So we'll show that if you can solve super heavy in space S, then can solve L2 heavy hitters in space O of k log k times S. So the second step will be that we can achieve S being a constant. Okay. So what is the super heavy problem? So super heavy is that an item is not just a heavy hitter. Heavy hitter means that like you're at least 10% of the L2 squared mass, so you're at least 1% or whatever. Super heavy means that you're not just 10% of the mass. You are almost all of the mass. You are like 99.9% of the mass. Okay. So super heavy says super heavy if xi is, let's say, bigger than 1,000 times the sum of j not equal to I of xj squared. So that's the definition of super heavy. Okay. So if it had been in an L1 sense, if it had been in an L1 sense, then what it means is like literally 99% of the things you see in the stream are I. Here it's an L2 sense, so it's not so here, like, give you an example. Let's say you have a stream with n elements. One item appears 100 root n times, 100 times the square root of n times. All the other items appear once. So the total length of the stream is n. Now, the mass of that item that appears 100 root n times, well, when you, this should have been squared, sorry. When you square him, you get 10,000 n. Xi squared is 10,000 n. Whereas everyone else combined is only like less than n, right? So in a squared sense, he really dominates. He's almost everything. Does that make sense? So that's what it means to be super heavy, which is not the same as being 99% of the stream. It's being 99% of the stream, or 99.9% in an L2 sense, in a squared sense. Okay. So I'm going to show you parts 1 and 2. How do you reduce to super heavy? And then how do you solve the super heavy problem? Does that make sense?
Yeah.
So first, let's reduce. So I'm going to instant. So let's suppose, what is a reduction? A reduction is, if you reduce from problem A to problem B, what it means is if you have a black box that can solve B, then you can use that to solve A, right? So if we have a black box that solves super heavy, we can use it to, we can use that black box to solve actual heavy hitters. And actually, let me just say something here. The success probability just needs to be a constant here. If you can solve super heavy space S, let's say, with failure probability at most, let's say 1/10. Then you'll show that, and here it'll be with failure probability 1/poly k. So if you can solve super heavy with failure probability, 10%, heavy hitters problem with failure probability 1/poly k, where the exponent in the poly k can be however big you want. It will affect the constant factor in your memory. So what's the reduction to super heavy? So what I'm going to do is the following. Suppose I have a data structure that solves super heavy. I'm going to instantiate q copies of it. So I call this D1, D2, up to DQ. Each, I'm going to write it up here. Each DJ solves super heavy. I'm also going to have a hash function H, which maps the universe into 1 to Q. And it's from a universal hash family, or a pairwise independent hash family. So that means I can represent H in O of log n bits, which is just a constant number of machine words. And now, whenever I see I in the stream, I'm going to compute H of I, and that's going to send me into a random DJ, and it'll be processed there. Okay. So now, what can I say? So if you pick Q to be like very big. I mean, this constant is not the best possible constant, but pick Q to be like 1,000,000 times K. Okay. Let I be a heavy hitter. There are only K of them, right? There are only K heavy hitters, because heavy hitter means approximate top K. So let I be a heavy hitter. The probability that I is isolated from other heavy hitters by H, I claim is actually quite high, right? Because what is the expected number of other heavy hitters that collide with I under H? What's the, if you look in here in this bucket, how many other heavy hitters landed there? Well, in expectation, it's K over Q, right? So you expect K over Q. K over Q is 1 in 1,000,000. So you expect less than 1 over a million. So what's the probability that you have at least one? The probability that you have at least one is by Markov's inequality. Well, that's the probability that you're a million times bigger than your expectation. So that's rare, right? That's going to happen with probability at most 1 in a million. Okay. So now, what's the probability that, okay, again, let's look at now the L2 squared mass from the non-heavy hitters. So what's the probability of the sum over J in tail K? Okay. Tail K means not the heavy hitters, not in the top K, of xj squared. So, okay, let me write it like this. So I'm only going to keep track of the L2 squared mass that collided with I under the hash function. So xj squared times, let's say, an indicator random variable for the event that h of I equals h of j. Okay. So this summation just means how much squared mass from the non-heavy hitters is colliding with I in its bucket. Okay. So you expect this thing to be at most x tail k squared over q, which is like 1 over a million times x tail squared over 1 over a million. So okay, so yeah, so what's the probability that this is bigger than, let's say, I don't know, 10 times its expectation, where its expectation is at most x tail k L2 norm squared over q. This is at less than 1 over 10. This is just Markov's inequality. I mean, by the way, this was also Markov, right? And this, just by definition, is equal to 1 over 10 to the fifth times x tail k squared over k. Okay. So with the probability that you're not isolated from all the other heavy hitters is 1 over a million. The probability that there's too much light mass in your bucket is at most 1 over 10. If these two events, if neither of these two events happen, you will be super heavy, right? Because by definition, if you're a heavy hitter, you are bigger than 1 over k times x tail k squared. And I'm saying that the remaining light mass, the noise in your bucket, is a 1 over 100 times, is with high probability only a 1 over 100,000 times smaller than that. Does that make sense? So, so actually, let me write it like this. If this had said not isolated, then this would be less than 1 over a million. Okay. And if neither event happens, then I is super heavy. And the probability of neither happening, the probability that one of them does happen, let's say, is at most 1 over 10 plus 1 over 10 to the sixth, which is like much less than 1, right? So that means with high probability, with probability pretty close to 1, any fixed heavy hitter will be super heavy in his bucket. And if he's super heavy in his bucket, you will find him with probability 99% because your failure probability over here is at most 1/10. So overall, what this means is like for any heavy hitter, if you look at the bucket where he landed, he will be reported with probability at least 70% or something like that. Okay. Okay, so that's a start. But that's not exactly what we want, right? To solve heavy hitters doesn't just mean that each individual heavy hitter is found with probability 70%. We really want to find all of them with good probability, not just one, but all k. There could be k of them. We want to find all k of them. So how do you get that done? And that's also kind of a simple trick. What you do is you just repeat this picture many times and then do kind of a turn off and union down. So let me just write it down. So okay. So we're going to repeat this. Let's call it R, which is theta log k times. And each one of these, this is like, let's call it D11, D12 up to D1Q, D21, D22 up to D2QQ, etc. This is DR1 up to DRQ. And then each one has its own hash function. H1, which maps N into Q, all the way down to HR, which maps N into Q. Okay. And then I'll return as our list of heavy hitters L, which is defined to be the set of all I, such that I is returned by at least, let's say, R over 2 Dij. I'm already using I. D's. Okay. So that's the reduction. First of all, if you just remember the promise, what does it mean to solve heavy hitters? It means with good it means A, your output list has size at most O of K. And B, with high probability, you do not have any false negatives, meaning if someone is a heavy hitter, they will be included in the output list. You're not allowed to miss anyone. Okay. So this L has size O of K by construction, right? Why? Because the number of D's in this grid is Q times R. Okay. And you're only returning someone if they're returned by at least R over 2 of the data structures D. Well, there are Q times R of them. Each guy you return consumes R over 2 of them. So the number you can return is guaranteed to be at most 2Q. So L is guaranteed to be at most 2Q in size, which is O of K. So that's good. Now, what about the other thing, which is you're not allowed to have false negatives? Well, look at a heavy hitter. What we argued on the last slide is if you look at where he lands in the first row, with high probability, with probability 70%, that data structure will return him. Okay. So now, what's the expected number of, so again, also that's true of the second row as well. Look in the second row, the data structure he hashed 2 there. With 70% probability, that data structure will return him as well. So the expected number of data structures that return him is going to be something like at least 7/10 times R, because 7/10 of the rows will return him. Okay. So what's the probability that he's returned in less than 5/10 of the rows? Well, that's a deviation from the expectation by like 2R over 10, right? And the probability of that happening by the Chernoff bound is exponentially small in R. We chose R to be log K, theta log K. So that means the probability that you fail to return that heavy hitter is 1 over poly K. So by a union bound over all the heavy hitters, there are only K of them, you will not have any false negatives with high probability. Okay. Now, again, here you have Q times R data structures that you're instantiating. Q is O of K, R is O of log K. So you have O of K log K data structures. And you also have R hash functions, but each one of those is pairwise independent, each one only consumes a constant number of words of memory. So you're using O of log k words of memory for the h's, and then an additional O of k log k times s memory for the k log k copies of this data structure. So that's where the k log k times s comes from. Okay. So any questions about that before we actually then now show the main event, namely how do you actually implement this data structure in constant memory? Okay, so I guess people seem to be okay, or at least no one is speaking up. So I'll assume that people are okay. So that's it for the reduction. So now we'll show S is a constant. That can be achieved. And this is where we're going to use our newfound knowledge of Dudley's inequality and bounding the suprema of stochastic processes and Rademacher processes. So here's the idea. So, and I should say in the reduction, like there are some buckets that might not have any super heavy item in them, but we don't care. If there's no super heavy item, we allow the data structure to return whatever it wants. It doesn't affect the correctness argument from the previous whiteboard. So let's just assume that there is one, because if there isn't one, we can do whatever we want anyway. So there's some super heavy, I'll call it H, which is a number between 1 and n. And I can write H in binary, right? So this is H0. And our goal here is going to be to learn the bits of H one by one. So we're going to learn the H, we'll learn HJ one bit at a time. Or we'll learn H one bit at a time. So first I'm going to state a lemma, and this lemma is really the heart of the argument. And we're going to spend some time proving the lemma. The lemma let yt be a histogram, the state of the underlying frequency vector at time t. Let so we're going to look at that y0, y1, y capital T be the evolution of y over time in an insertion only stream. So what does it mean for a frequency vector to evolve according to an insertion only stream? It means that if you look at two adjacent time steps like y5 and y6, the only way they can differ is that y6 has one more in one of its entries, right? You saw an item in the stream, you incremented that item's coordinate by 1. So the difference between yt and yt minus 1 for any t is some standard basis vector. Okay. I don't know if this is clear or not. This word here says evolution, be the evolution. So my handwriting kind of sucked. Okay. Now, let sigma 1 up to sigma n be 4 y's independent plus minus 1 random variables. Then, if you look at the expectation of the soup over all time, of the absolute value of the dot product of sigma with yt. This is at most up to a constant factor, the L2 norm of the final vector. Okay. So I want to spend just a little bit of time helping you digest what this means before we use it. But I mean, we do know the following, right? So this is what I said. I said the expectation of soup over all time of sigma dot yt is at most the final norm. Okay. So that's the main claim, where the signs are only fourwise independent. Now, forget about the soup. What is the expectation of just like sigma dot z? Right? This is an expectation over sigma. By Cauchy-Schwarz, right? This is just the sum of sigma I zi. By Cauchy-Schwarz, this is at most the expectation of that thing squared, square root. And if you do that, you're going to basically have like the sum over all ij of zi zj sigma I sigma j. Again, the off diagonal terms, expectation of sigma I times expectation of sigma j is 0. The only thing that survives are the diagonal terms, and you're going to be left with sum over I of zi squared. And then you have a square root. So this is just equal to the L2 norm of z. Okay. So if you look at any individual dot product, the expectation of that dot product is at most the norm of the vector. But this is not just talking about the expectation of one dot product. It's talking about the expectation of the max of all the dot products. Imagine that they were not random signs, but they were Gaussians. What I'm going to talk about, by the way, will hold for Gaussians too. But imagine that they were Gaussians. So if you have one Gaussian, if you have not just one Gaussian, but a lot of Gaussians, capital T Gaussians, and you take the max of them, what do you expect? What's going to happen in expectation? You're gonna have an extra factor of the square root of log capital T, just by a union bound, right? You're gonna want a union bound over all time steps. That's gonna make you pay square root log capital T, right? And you can do the same kind of reasoning for any sub-Gaussian distribution, including Rademacher's. So the thing that would have been just basically obvious from a union bound would be if I had an extra square root log t here. That would be obvious from a union bound. But what the lemma is saying is that you actually don't need to pay that square root log t factor. So that's the significance. That's the significance of this lemma. The fact that you don't need to pay anything to do a union bound, right? You just have a constant out front. So it's as if there was just a single random variable there. You paid absolutely nothing to be able to say that all capital T of them are small simultaneously. An example is, what if your stream was 1, 2, 3, 4, 5, etc. What does that mean in terms of the y's? That means that y0 is the 0 vector. y1 would be 1, 0. y2 would be 1, 1, 0, etc. So if you look at sigma dot y, right? Sigma dot y1 is, well, it's going to be sigma 1, right? So sigma dot yt is going to be equal to the sum j goes from 1 to t of sigma j. So that means that, for the first t minus 1 steps, you were, imagine that you start at the origin. You're a person standing on the number line. Initially, you're standing at the origin. Now you see sigma 1. That means you'll either walk left 1 step or you'll walk right 1 step. if it's -1 or 1. Okay, now you're where you are. Now you see sigma 2. That's going to make you also walk left 1 step or right 1 step. So sigma dot yt is basically your position at time t after doing a random walk on the line for little t steps. This is equal to the position after t steps of a random walk on the integers, starting from the origin. Okay. And kind of Lovey's maximal inequality says the expectation over the random choices in your walk of the max absolute value of any position reached is at most some constant times square root of t, which, by the way, is just equal to the L2 norm of y capital T. So I don't know, some of you may have heard of Lovey's maximal inequality or not. I mean, it's something that is usually taught in, I don't know if it'll be taught in like the very first probability class you take, but if you take enough probability classes, you'll see it at some point. It's kind of a standard thing that people study in probability, these maximal inequalities. And kind of the lemma generalizes, just by, out of curiosity in the chat, anyone who's heard of Lovey's maximal inequality, or maybe you didn't know the name, but anyone who's heard of this fact that if you do a random walk on the line, your maximum absolute value is bounded. You basically always stay in a pretty small interval between minus O of root t and O of root t. So I'm curious, anyone who's heard of that, just write it in the chat. Okay, so at least one person. So this lemma is a generalization of Lovey's maximal inequality in two ways, right? One is that it works for an arbitrary evolution of an insertion only stream, not just the stream 1, 2, 3, 4, 5, but any insertion only stream. That's one way it generalizes Lovey's maximal inequality. Maybe the more surprising way it generalizes it is that kind of the typical proofs, there's this like reflection principle proof of Lovey's. The typical proofs very crucially use the fact that your decisions, your random decisions over the time steps are independent of each other. What you decide to do in time t is independent of everything you did in the past. That's not true for our lemma. Our lemma says that these sigmas are only fourwise independent, right? So already this lemma says that Lovey's maximal inequality holds even if your increments are only fourwise independent. And I should mention, maybe a little advertisement for this course, three-wise independence doesn't suffice. Oops. And that was due to Narayanan in 2019. And that was actually, he took a previous version of this course in 2018. And this was not his final project, but he worked on it after the class was over and managed to show that the fact that we used fourwise independence in our proof is really necessary. He showed that, well, first what he showed was that two-wise independence doesn't work. He constructed a two-wise independent distribution for which this lemma fails. And then after he did that, he later generalized his idea and showed that even three-wise independence doesn't work. Three-wise independence also fails. You really need four-wise independence. I mean, it doesn't really matter for us. The only reason you're going to see in the design of the algorithm, the only reason I want to get away with four-wise independence is because I can store a four-wise independent hash function in a constant number of words of memory. But that's also true for 8-wise independence. It's also true for 42-wise independence. As long as I'm using constant-wise independence, it doesn't really matter whether it's 2, 3, 4, or 50. Okay, but it just turns out that 4 works, and 4. Why is what true? The fact that 4-wise independence uses a constant number of words of memory. So I think in the past, is that the question?
Yeah.
So earlier when we talked about KY's independence, we said you can like if you have a if you have a bunch of KY's independent bits, and there are n of them, you can generate them using k log n bits of memory. But for me, a machine word can hold log n bits. Sorry, I didn't say that explicitly. When I say machine word, I'm assuming that the machine word can store log n bits. So k log n bits is k o of k words. So if k is a constant, o of k is o of 1. Does that make sense?
Yeah. I didn't realize machine word was like login.
Right. Yeah. Sorry, I didn't. I never. I never. I never said that explicitly. Okay. So good. So now let's try to develop the algorithm using this lemma. So as I already mentioned, we're going to try to learn h bit by bit. So how do we learn h0? So learning h0, what I'm going to do is I'm going to draw sigma 1, sigma n. Each one is a random sign from a 4-wise independent family. And I'm going to instantiate just 2 counters. And let's also say, let's say we know the stream length. We know the stream length L, and we also know the frequency of H at time L. Okay, these assumptions can be removed. Okay, of course we don't necessarily know these things, but instantiate 2 counters, not counters. Of course, we don't know the final frequency of H, but it's just going to be easier to explain how the algorithm works if we did know that, and then I'll talk about how to remove that assumption so that you don't need to assume that. But for now, let's assume we know it. Okay, I'm going to instantiate 2 counters. Let's call these counters B0 and B1. And let's say I see I in the stream. I'm gonna see. So I see I in the stream. I looks like 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1. And this is bit number 0, this is bit number 1, this is bit number 2, this is bit number 3, all the way up to log n. I'm trying to learn the 0th bit, right? So I see I in the stream, and I is a 1. I mean, the 0th bit is a 1. So what I'm going to do is I'm going to update B1. Right? Because it ends in a 1, I'm going to update B1. And what I'm going to do is let's say I'm going to add sigma I here. That's it. That's how I process an update in the stream. Okay. When I see I in the stream, I look at its last bit in binary, its 0th bit, and I update the corresponding counter by sigma I. Okay? That's it. Of course, this is all part of a larger reduction, right? If I'm actually trying to solve heavy hitters, I remember I had these log k different rows. Each one had a q different data structures that solves heavy hitters. So in actuality, in the actual heavy hitters algorithm overall, I'm gonna hash I log k different times. Each hash is gonna send it to a random super heavy data structure. Each super heavy data structure is storing its own sigma vector drawn from a 4-wise independent family. And then I'm going to do this picture inside of each one of those data structures. So now let's just think. So let's say, just for the sake of illustration, for illustration, say that H0 is 1. That implies that B1 is equal to sigma H times XH0 times XH plus the sum over all J not equal to H such that J is also odd of sigma J xj. And B0 is equal to the sum over all J even of sigma J xj. Okay. And I want to focus your attention on these two sums. Okay. Now, I claim that we can say something about these sums based on our lemma. Right? This is our lemma up here. What can we say? We can say that, I can define now, let me define two different vectors, y and y prime. Y is the frequency vector projected plus x, basically. X projected onto all odd j, which are not equal to h. And y prime is equal to x projected onto all the even j's. And the lemma says, so the lemma talks about the expectation, right? The expectation of the largest dot product you'll ever see. But if the expectation is small, then that means it's going to be small with good probability by Markov's inequality, right? If you say that this random variable in expectation is at most blah, the probability that it's bigger than 5 times blah is at most a fifth, for example, right? Or 10 times blah is at most a tenth. So the lemma implies that these two red boxes is that this red box, the first red box, let's call these 1 and 2. So red box 1 is at most y at the end of the stream, yl, which is at the end of the stream. And the second box is at most y prime l at the end of the stream, kind of with high probability, like let's say at least 80% or something. Let's say 90%. Okay. But now recall that, what do we know about x, about h? H is super heavy, which means at the end of the stream, the L2 norm of x at the end of the stream is equal to xhl squared plus yl L2 norm squared plus y prime l L2 norm squared, right? X, the L2 norm squared of x is just the sum over all coordinates of xi squared. So in particular, it's h plus the odd things excluding h plus the even things, right? And what do we know about super heaviness? This is almost everything. Okay. Does that make sense? That thing that I circled, xh squared, is like 1,000 times bigger than the other two things. Okay. Which means that, if you just take the square root, xh in magnitude is way, way, way bigger than the L2 norm of y at time L. And it's also way bigger than the L2 norm of y prime at time L. So these two numbers here are tiny compared to xh at time L. Okay. So again, this is big in magnitude, and this is tiny at time L, and this is tiny. It's not just tiny. Okay, so this is tiny always. That's my dilemma. It's not just tiny at time L, it's always tiny, right? The lemma says that over all time steps, you're always tiny. And this is always tiny. And this is big in magnitude. Big meaning much bigger than tiny. As soon as we've seen at least 1/10 of the total occurrences of H. Right? XH in an L2 sense, XH is like super duper huge at time L compared to the other two things. So, even if you've only seen like XH over 10 of his occurrences, he's still pretty super duper heavy compared to the other two things. Okay. And remember, we're assuming that we know X at time L. We know XH. We know XH at time L. Okay. So here's what I'm going to do. I'm going to wait. So I'm monitoring these two counters, B0 and B1, right? I'm going to wait until one of them is at least, so let's call this threshold delta. Delta is equal to XHL. I'm going to wait until at least, okay, I'm going to wait until some counter, one of B0, B1 is at least delta over 10 in magnitude. Okay. Actually, let me put it like this. Delta over 11 in magnitude. Doesn't really matter. Okay. Now, the claim is that once we've seen at least delta over 10 occurrences of XH, of H in stream, B1 will be at least delta over 11 with large probability. Does that make sense? Why is that? And the other claim is that B0 is going to be less than delta over 11, always. Okay. So this is just the lemma, right? The lemma says that B0 is always at most Y prime L, L2 norm, but that's way less than delta. It's way less than delta over 11. So the lemma directly implies that with the lemma combined with Markov's inequality implies that with really good probability, B0 will never be big. B0 will always be small. Okay. Furthermore, the lemma says, look, at the time when we've seen the delta over 10th occurrence of H, B1 will be large. Why? Because it's a large thing plus the very small thing. Okay. And yes, the small thing might have an opposite sign and might cancel a little bit of the large thing. But the large thing is so large compared to the small thing that even if you cancel a little bit of it, it's not enough to push it. It used to be delta over 10. It's so small that it's not going to push it below delta over 11. Okay. Does that make sense? So that's where the lemma is fitting into this argument. The lemma is fitting into this argument to say that these two things that I put arrows on are always small and they're never going to confuse you. You're never going to think that the wrong thing is big, or, it's very unlikely that you think the wrong thing is big. It's very unlikely that you think the big thing is small. Okay? Does that make sense?
Yeah.
Okay. Now so we're getting there. I haven't actually proved the lemma yet. We're getting there. How do you actually finish this off? Well, the problem is I did all of this to learn one bit of H. Okay. I consumed 10% of the occurrences of H in order to learn one bit of H. How many times can I consume 10% of the occurrences of H? Well, at most 10 times, because H only occurs 100% of its time, right? So that means that if I try to do this kind of argument, I could only hope to learn 10 bits of H. But H doesn't have 10 bits. It has log n bits. Right? So how can I learn all log n bits? Can only hope to learn 10 bits of H via such an argument. How can I learn all log n bits? So here's the intuition. Okay, this is not, of course, necessarily true because we're doing worst case analysis. But let's say that we're promised that the mass of the vector is randomly spread around. Okay, like someone came and just randomly permuted. They randomly permuted the indices of the universe before putting it in the stream. Now, let's say we've learned the first 5 bits of H. H0 up to H4 are 0, 1, 1, 0, 1, whatever it is. Now, that means that from now on, now we're trying to learn the next bit, the 6th bit. From now on, whenever we see an item in the stream, if that item does not end in, and I should say, like when you after you learn the 0th bit and you're trying to learn the next bit, what you're going to do is you're going to zero out the two counters B0 and B1, and you're going to kind of start from the beginning again. Not from the beginning of the stream, but you're going to restart the counters to 0 and just keep going from where you are in the stream. Okay. Now, what was I saying? I was saying that if you know that H ends in 0, 1, 1, 0, 1, and now you're trying to learn the 6th bit, whenever you see an item in the stream, if that item does not end in 0, 1, 1, 0, 1, you should not process it. You should just ignore it. Why? Because if it doesn't end in 0, 1, 1, 0, 1, you know that it's not H, right? Conditioned on the fact that everything you've done so far is correct, you know that the thing is not H. So by processing it and updating one of the counters, all you're doing is you're contributing to the noise, right? These 2 red boxes, you're contributing to one of those noise boxes. And like noise can only hurt you. Noise can only trick you into thinking that something is big when it's not big, right? So just don't do it. Just ignore this and move on to the next item in the stream. What's the advantage of that? The advantage of that is the fraction of the noise that survives is only a 1 over 2 to the 5th power now. Because, if mass is randomly spread around in the vector, because you randomly permuted the mass, the fraction of mass that ends in 0, 1, 1, 0, 1 is a 1 over 2 to the 5 fraction of the mass, which means that the noise is cut by a factor of 1 over 2 to the 5. Okay? So in terms of the survivors, H definitely survived. And what else survived? A 1 over 32 fraction of the noise survived. So H used to be 1,000 times bigger than everyone else. Guess what? Now he's 32,000 times bigger than everyone else, because the everyone else only includes the people who end in 0, 1, 1, 0, 1. And that's only a 1 over 32th fraction of the mass before, right? So he became even more super heavy than it was before. So when you're trying to learn the kth bit, he's not just 1,000 times bigger than everyone that's remaining. He's 2 to the k times 1,000 times bigger than everyone remaining. Okay, which means basically what it means, if you kind of think about it for a little bit, what it means is you don't really need to consume 10% of his occurrences to learn his next bit. You can get away with consuming something like 5% of his occurrences. Okay. And then the next time you're trying to learn a bit, instead of having to wait for 5% of his occurrences, you only have to wait for 2.5% of his occurrences. So when you add up how many of his occurrences you consume before you learn all of his bits, it adds up to less than 100%. It's a convergent sum. It's a geometric sum. Okay. So you will be able to learn all of his bits before the stream ends. So that's the basic idea. Now, of course, the mass is not randomly spread around. So how do you fix this? The way you fix it is, we didn't really talk about it. We talked about 2y's independent hash functions. There's also such a thing as 2y's independent permutations. So you can pick a pseudo-random permutation that's random enough that it makes this argument go through. Okay. So let me not get into that because we only have 7 minutes left, but that's the idea. Okay. So that, and then now the things that remain are A, how do you prove the lemma? And B, I made this assumption that delta, right? I said that you know the final value of xh at the end of the stream, but you don't actually know that. So how do you fix that? Problem, you don't know the final value of xhl. So, we had this threshold where we wait until one of the counters is delta over 11, but we don't know delta. So the fix is to observe that, first of all, xhl is roughly the same as xl L2 norm because it's super heavy. So we just need to know this. And we don't even need to know it exactly. We just need to know it up to a factor of 2. That turns out to be good enough to make the whole argument work. Okay, but we don't know that either. So what do? We run an AMS sketch on the side. Okay, so actually, let me write this. We guess in parallel that the final value, so let's call this alpha. We guess that alpha is equal to 2 to the 0, 2 to the 1, up to like 2 to the, let's say, 10. We make 11, some constant, parallel guesses for alpha. And then in parallel, we run this entire algorithm that I just told you for super heavy. We run it assuming that delta is alpha. Okay. And then also in parallel, we run the AMS sketch. Okay. So now what's happening? So we're running all these parallel guesses for alpha, and for each one, we're running the algorithm assuming that delta is alpha. We're also going to run an AMS sketch. If you don't remember the AMS sketch, it approximates the L2 norm. Okay. Now, the sloppy thing to do would be make the AMS sketch, boot it up with a failure probability that's so small that we can union bound and say that the AMS sketch never fails throughout the stream. Okay. And then at every time step, we can ask the AMS sketch, what's the L2 norm now? What's the L2 norm now? What's the L2 norm now? And at some point, it's going to say, oh, well, it's the L2 norm now is like roughly 6. And you're like, oh, it's 6. That means that our guesses of alpha being 2 to the 0, 2 to the 1, and 2 to the 2 were off. It's roughly 2 to the 3 or bigger. So let's just kill our parallel instantiations that guess 2 to the 0 and 2 to the 1 and 2 to the 2. And let's boot up another parallel instantiation that guesses that it's 2 to the 11. Okay. Now, that new parallel instantiation that guessed 2 to the 11 it missed a prefix of the stream. It missed the first part of the stream. However, the first part of the stream had at most 2 to the 2 mass in it, which is way smaller than 2 to the 11. So if the right answer actually ends up being 2 to the 11 or larger, the mass we missed is insignificant compared to the final number of occurrences of xh anyway, of h anyway. So we didn't miss much. Okay. So that's the idea. We're always going to run 10 or 11 parallel guesses. And then once in a while, we're going to kill the really small guesses once we know they're wrong. And we're going to boot up a parallel instantiation that has a larger guess. Now, what about item 3? I said that we're going to keep asking the AMS sketch every time step, what is it now? What is it now? What is it now? The naive way of making this work is to make the failure probability be really small so we can union bound over all these time steps. The problem with that is if your failure probability is delta, you pay a log 1 over delta in your number of words of memory. I don't want log 1 over delta words of memory. Delta is going to end up being something like 1 over the stream length. So I'm going to pay log the stream length in terms of my memory bound. I don't want log stream length. I want constant memory. So then what you do is you prove that lemma that I showed you, which is based on supremum stochastic processes, you prove a similar lemma applied to the AMS sketch. You prove that if you run the AMS sketch at every time step, you query it at every time step, the maximum error it will ever give you with high probability is big O of epsilon times the L2 of the final vector. So you don't need to pay to union bound over all time steps. It's sort of like the lemma again for free. Like for free, your maximum error is never larger than epsilon times the largest L2 norm. Okay. So that's how to fix the algorithm. Now the only thing that's left is how to prove the lemma. Okay. So any questions? I think we only have 2 minutes left. So I'll be able to sketch how to prove the lemma. And I'll either finish it off on Monday or put it in the notes. Okay. But any questions before we now talk about the lemma? So this said that the expectation over sigma of the sup over all time steps of sigma.yt is at most y capital T L2 norm. Okay. So first of all, because I have so little time left, I just want you to see the idea in lecture, and then maybe I'll put the details, the full details in the lecture notes. But what's the idea? Let's look at the special case where the stream is 1, 2, 3, 4, 5. So that means that yt is 1, 1, 1, 0, 0, t times. And let me define vt to be yt over the square root of capital T, which implies that for all time steps, vt has norm at most 1. Okay. And let me define now, A is equal to the set of vt over all time steps. So we want to show that the expectation over sigma of the sup over x in A of sigma dot x is basically a constant. That's what we really want to show. This is exactly what we talked about before on Monday. This is the supremum of a Rademacher process, which, Rademacher satisfy the Khinchin inequality just like Gaussian. So everything I talked about last time applies. Dudley still holds. Generic chaining, all that still works. Okay. So we know that the expectation over sigma of the sup over x and A of sigma dot x is at most the sum over all r from 1 to infinity of 1 over 2 to the r times square root log of the covering number of A with respect to the L2 norm, 1 over 2 to the r. So the name of the game really is just understanding how big is an epsilon net of A. So an epsilon net of A, just notice that if you look at some v at time A minus v at time B, this is going to be some vector that looks like it's going to have a bunch of zeros here. It's going to have some ones. It's going to have some zeros. And then there's a division by root t, and you're taking the L2 norm of that. How many ones do you have here? And let me just say it. It's A minus B. So this is equal to a minus b over root t. So the claim is that if you take an epsilon out of a with respect to the L2 norm, this is at most 1 over epsilon squared. Why is that? The proof is just take the following net. V at time 0, V at time epsilon squared t, V at time 2 epsilon squared t, V at time, V at time, whatever it is. Epsilon squared. I guess what? Yeah. So at time, 1 over epsilon squared times epsilon squared t. That's it. So maybe epsilon squared plus 1 or something. So that's the proof. Okay. And then now you just take that and you just plug it directly in there. And you get that the expected soup is at most the sum over all r from 1 to infinity of 1 over 2 to the r times square root log 1 over epsilon squared. So square root log of, I guess, 2 to the 2r. 2 to the r squared is 2 to the 2r, which is at most the sum over r of root r over 2 to the r, which is a constant. So Dudley's inequality gives you exactly what you want. And okay, again, we're basically out of time, but let me just say the following thing. Okay. Now, how do you get this to work not just with full independence, but four-wise independence? Because we only have four-wise independent random signs. The point is, why did we have a square root log here? We had a square root log because sigma dot x decays like e to the minus lambda squared because of Khinchin's inequality. And square root log is like the inverse function to e to the minus lambda squared. But if we didn't decay like e to the minus lambda squared, but instead we decayed like 1 over lambda to the 8th or something, then instead of root log, you would have like the raised to the 1/8 power function. You would have the covering number raised to the 1/8 power, right? Which is still enough to make this whole thing converge. And if you really pay attention to what you need to make this whole thing converge, it turns out that what you really need is four-wise independence. And if you have four-wise independence, it'll converge. Okay. You won't get root r over 2 to the r, but you'll get some other thing that shrinks fast enough that it converges. Okay. So it's all basically Dudley's inequality. So any questions about this? And if you want to extend this not just to a random walk on the integers, but an arbitrary insertion only stream, you basically just need to prove that this claim still holds, even under an arbitrary evolution of an insertion only stream. But it does. You can show that. It's honestly not that much harder than this example to show it. Okay. So I think I'll stop recording now. If anyone has questions, please let me know.
Professor, I had a question. So I think for like the L1 version of this problem, you can just use like the super majority voting algorithm, right? Like, why is the L2 version so much harder? Like, what fails when you just use the majority voting algorithm to try to find